Welcome everyone to another Meyer Sound webinar. How's the transmission? Can you hear me? Can you see me? This is the third webinar in a series of webinars that focuses on real-world phenomena. So without further ado, let's get started. I'm going to start sharing my keynote and introduce today's speakers. Please stand by. Hopefully everybody can see the screen. Today is going to be all about impulse responses. As I said before, the third webinar in a series of webinars about real-world phenomena. And all of these webinars, upon conclusion, can be found in our YouTube Thinking Sound channel, which I will talk about a little bit later, because you, as we speak, are joining us exclusively through the Meyer Sound user community, where we like to stream our webinars live. And currently it's counting over 10,000 members, which is awesome. Thank you for joining us, and please spread the word. As I said, all webinars, including the one today, will be available upon conclusion on our Thinking Sound YouTube channel. And with that, I'd like to introduce today's speakers, starting with Mauricio Magu, Ramirez, Meyer Sound Senior Technical Seminar Instructor. Magu, are you with us?
Yes, hello Marlene, hello everybody.
Excellent. We're also joined today by Oscar Barrientos, Meyer Sound Technical Services Manager for Latin America. Oscar, how's the transmission?
It's good, and it's a pleasure again to be here with you.
Wonderful. And we have a third lecturer today, none other than Juan Lozano, Meyer Sound Test Engineer. Juan, how's the connection?
Hey, how's everybody going? Thanks for the invite.
We're happy to have you. So as always, I'm honored to give you a brief overview of what we're going to talk about today. We're going to have an introduction, which is the thing that we're doing right now. And then Magu will look at where is the impulse response coming from, followed by diving into the impulse response, which is what everybody calls it colloquially, although we like to think of it as the inverse fast Fourier transform. What about the time range and amplitude range of impulse responses and how to interpret them? Level can be seen on a linear scale and a logarithmic scale, and we're going to talk about that today, as well as polarity, what happens if you reverse polarities, reflections and interactions with the room and other loudspeaker, and then finally some real-world examples that focus on main system in conjunction with side fills or front fills or delay or relay systems, and if time allows for it, we will have some Q&A afterwards. If you have any questions, please put those in the comments of the Facebook live stream. I will be monitoring those. And without further ado, I would like to hand it over to Magu.
Well, please advance one slide, Marlene. And then what we will see here, it is a short video. It's 10-second video that will have pink noise. And we will see pink noise in 4 different ways. Marlene, you stop sharing.
Yes, because I temporarily need to make sure that everybody can see you as well. Okay. So please stand by while I'll start to share the keynote once more. Okay, first clip coming up.
Okay, so can you stop for a moment? Okay, I have to explain everybody what we will see here. So every one of the clips will be 10 seconds and we will play pink noise, but the pink noise will have different file size. In this one, it's a 1 second file of pink noise wave file, and we will see in the upper right, in the upper left, the audio editor where I dropped the 1 second file of pink noise. You can see that it reads 48 kilohertz, 16-bit. Into the right, we can see how the pink noise looks in a real-time analyzer, theory octave basis. In the bottom left, we can see how the pink noise in a 20 milliseconds time window, it's been displayed. And in the bottom right, we will see the pink noise as in a fast Fourier transform analyzer looks. Okay, so please play. So it's interesting because we can listen to the pink noise, but we can observe how the pink noise looks in different machines. Okay, in the next video, we will see, but instead of 1 second of pink noise, what we will see is 10 millisecond file of pink noise, and this 10 millisecond file of pink noise will repeat. So we will listen this during 10 seconds, but the file is 10 milliseconds. And what you will discover is that 10 milliseconds of pink noise is not be here as pink noise anymore. And please play. So it's interesting because right now, since the time period of 100 hertz is actually 10 milliseconds, in the fast Fourier transform analyzer, we can see lines and we can listen frequencies every 100 hertz. So every 100 hertz is a line, so you can see in the bottom left, in the bottom right, 100, 200, 300, 400, etc., etc. So this is a shorter version of pink noise, and right now we are missing frequencies below 100 hertz, but also frequencies in between every 100. So we cannot hear and we cannot see 101, 102, 103, just frequencies every 100 hertz. Remember that the original file is pink noise. So in the next video, the file will be only 1 millisecond and will be played again in a loop, and this will be 10 seconds of the file. And because 1 millisecond is the time period of 1000 hertz, what we will hear is basically frequencies every 1000 hertz, starting in 1000 hertz. Please play. It's interesting to learn that maybe it's hard to believe that the original file is pink noise, and we are thinking, where are all the other frequencies are gone? Well, basically, the file is only 1 millisecond. The file can contain only frequencies every 1000 hertz. So the next one, it's very interesting, and it's exactly what will make us, in some way, start to understand about the input response. Because in the next one, what we will play is only one sample at maximum amplitude from a 1 second file. So what I did here is I take all the samples of the pink noise and turn down 90 decibels, but only the center sample, the sample that corresponds to 0.5 seconds, maximize the level. So what we will listen and what we will see is very interesting. Please play. So you can see that for a brief moment in time, basically every 1 second, because the file is 1 second, the oscilloscope display a peak that it's only there for a brief time, and the fast Fourier transform shows that all frequencies raise at the same level. So this means that that single sample, when played, contain all possible frequencies. And in the real-time analyzer, we can see a raise in the bars with a tendency of 3 decibel per octave in the amplitude increase from low frequencies to high frequencies. Okay, so next slide. And for the next slide, we will learn where the input response is coming from. And for this, we need a person that has the knowledge, really depth knowledge, and also the strong capacity to explain a really complicated topic. So Juan, it's your turn.
Hello, everybody. So I think I need to share my screen for this part. Let me try it. Let's see. Can you see this? Everything okay?
Yes, sir. We can see your
Perfect,
screen.
yes.
All right, so here we have, I wrote a small program to show this and to exemplify what's going on with the impulse response. And
What do you have in the different three displays, Juan? Can you explain?
yes, so on the top left, there's an oscilloscope. On the top right, there's like a bunch of code that I'm gonna be like switching back and forth on different settings. And on the bottom part, there's like a very special thing that's a bank of oscillators where each one of them have like, each one has like a different frequency. So the first one has zero frequency, 0 hertz. Then the second one has some frequency, the base frequency multiplied by 1. The third one has the base frequency multiplied by 2, and so on and so on. So if I go to number 6 or something, we should be able to see some sinusoid of some multiple of the original frequency. And at the very last, we have some sinusoid that has like, here we're displaying the digital samples and the analog samples. So the digital samples, we know that this frequency is the Nyquist frequency because we have 2 samples per oscillation. And now the interesting thing is also that I can display some frequency and change its phase. So it's a very controllable bank of oscillators where we can see how they all are going to add up together. Now, the idea is that if we zero them all out, now everything is muted, the phases are all in 0, then we shouldn't see anything. But if we open this other setup, all right, now I have an impulse. So it's interesting to see that this shape of the impulse response or any impulse is just generated by summing a bunch of different sinusoids with very specific phases. And even more interesting is that this analog version of the impulse is a band limited impulse because it only has like a limited amount of sinusoids. So the digital version sums up correctly, and I can hide the analog one. Oops, sorry. Can hide the analog one. We're gonna see that, oops, we shouldn't be seeing this. All right, we're seeing that it's a perfect impulse, but in reality, the analog version is a band limited impulse. So even more, we can do funny things with this. We can change, for example, the phase of one of the sinusoids, and we're gonna see that this arrangement of sinusoids is very sensitive to small changes. Once we change something, it's no longer an impulse. So the interesting thing is that now we can think of this bank of oscillators as sort of the magnitude response and the phase response as we see them on SIM or any dual FFT analyzer. Now I can set the oscillators to the specific magnitudes and phases of some frequency response of a filter, and we should be able to see interesting things. Let's see. So this looks much more like a second order Butterworth filter. This is the impulse response that was generated by summing a bunch of sinusoids on the perfect relationships of magnitudes and phases to produce the correct outcome. Let's see. So there's even a couple of interesting side effects of all of this arrangement. Now, if I show more time, 20 milliseconds, you can see that there's like a repeated version of the impulse on the, like to the right and to the left. We can see multiple copies of that because we're just summing sinusoids. So we're summing enough sinusoids to cover this space, but that will imply that there's going to be some periodicity on this impulse response. And that's actually a property of the inverse FFT. So an inverse FFT would create like the impulse response on one block, but if you extend those sinusoids further to the right or to the left, you're going to get many more repetitions of the same thing. Let's go back to this. What do you think about that, Magu?
It's very interesting, Juan, that if we are trying to define about the impulse, basically for what I see right now, all frequencies should be played at the same amplitude, but also all frequencies should be played simultaneously, because for what I can see here, some of your sliders, the sliders in the right has less amplitude. So this looks like a low pass filter from my experience measuring devices with analyzers. But also I can see in the bottom ones that the phase is shifting down in the sliders, similar to what a low pass filter is doing. So as soon as you remove all the level differences and the time differences is when I see that the impulse becomes very thin, very narrow, and very big in amplitude. So that is the reason that when I measure in the analyzer that single sample, it contains all frequencies. And I see only one peak because all frequencies are played simultaneously in time because this is no time offset. It's very interesting, Juan. Thank you very much.
Let me show you a couple of other things. So here is the second order Butterworth filter. Now we have a fourth order Butterworth filter. And you can see that this it has a longer impulse response. And if we keep pushing it, now we have the phase response expected from a fourth order Butterworth filter. But if we keep pushing it, something very interesting is going to happen. And that is that the tail of the impulse response is no longer, it can no longer fit into the amount of time that we're being able to analyze. So if this thing goes and wraps around, we just talked about the periodicity of this process, but it's also like related to why, if the impulse response is too long, then the coherence on a dual FFT analyzer starts to drop because it no longer represents what we were expecting.
Belongs to the FFT side. Yes, but what we see right now into the left, in the top left graphic, actually is what continue to what we see in the right. Typically, when we use analyzer. And this is because an 8-order filters introduce so much phase delay that your 10 milliseconds time window is not enough in the oscilloscope to contain all the phase delay. Yeah, very, very interesting.
Now let's make it a little bit more extreme. Let's add 3 samples of delay. I can add that over here. You're gonna see that, whoop, it moves to the right, and you can see that it literally is like a cyclic version of the impulse response. If you keep moving to the right and to the right, and you see that the phase is increasing, the slope of the phase is increasing, it starts to show up on the left. And even more interesting, you can also do zero delay, and you can also do, let's remove the phase from this impulse response. So let's create a zero phase version of that. It's like a linear phase version, but it's centered at the initial position of the initial impulse response.
Okay, so Juan, this is for my experience measuring devices. This looks like typically an FIR filter, and normally I see symmetry between what we see in the tail to the right, but right now this is also a pre-tail in the left. And this is because in order to have phase zero, there should be a symmetric filter in terms of time. Very, very interesting.
And obviously, we cannot use this type of filter because if we assume this is time zero, we cannot get signal before the input of the signal. So what we need to do is actually just add
compensate time,
some delay to the impulse response so that we can have a linear phase version of the impulse response that starts in the, it is delayed by some amount so that it can actually be realizable in a real system.
Yes, that is the reason that we see latency every time we use FIR, and the lower we want to do, let's say, a low pass filter, the latency is larger, because in order to, I don't know, to localize where is the first moment in time, the first moment in time is several samples earlier than when we see the peak. Very, very, very clear.
So, and Juan, by definition, we can tell that the FIR filter is not having the delay because itself, but because we need to see the complete input response, right? Something like that.
Exactly. Yeah. So, and it's an interesting distinction because, like, we can also implement a minimum phase FIR filter. It's just that that's not the thing that is interesting about FIR filters. The interesting thing is that we can make them linear phase. So it's not actually the fact that it's an FIR filter, but the fact that we want to make it linear phase. One final example over here, I'm gonna make the phases random, and you're gonna see that it's just gonna be a little bit of a mess because it no longer represents an impulse. It's just like, what is going on here? It's just all messed up because the phases are not aligned in a proper way to create the peaky shape of an impulse. So it's an interesting thing that all of these, like Butterworth filters and all of that, they have a very specific phase relationship that can produce exactly that impulse.
So Juan, you mentioned that there are linear phase filters, and what is the other name?
Minimum phase?
Minimum phase filters is basically what I think is the standard filters, and linear phase is the ones that this all phase is at 0, and this is we can call a chaos phase because every oscillation has random phase. Okay, and in this way there will not be a syncing time as what we can see. This is many of the frequencies are time aligned, and this is the reason that we can see a peak. Oh, thank you very much. Yeah.
One final detail just to push a little bit the curiosity on this topic. I'm gonna blank everything now. I'm gonna go back to 0, blank, okay. And now I can raise the last sinusoid, the Nyquist frequency. And it's an interesting idea that we tend to think about the Nyquist theorem as at least twice the highest frequency, but it's more than twice. And it doesn't include the Nyquist frequency exactly because something that is very obvious in this case. So this is just a sinusoid, and we can see that we can recover the sinusoid because we have 2 samples per period. The problem is that if I move the gain of the sinusoid, we see this behavior. And if I move the phase of the sinusoid, we see exactly the same behavior on the digital samples. And that's a very interesting thing. I'm gonna
Juan, can you keep only the one that is in color? That is, I guess, that is digital. That's the sample. Can you move the gain? Let's say like -6 decibels. So -6 decibels from your peak. Your peak, what is the level in your when the slider goes to the top? What is that?
The peak is let's set that so that we can go 0.5. All right.
Okay. Right now we have that in the scale in 0.5. If you turn it down 6 decibels, it will be 0.25.
Correctly.
Okay, that's correct. Okay, go back to 0. No, go back to when the okay, that is 0.5. Now I am trying to get, but if you move the slider 120 degree, it should be 0.25. Oh no, maybe it's just 90 degree.
Yeah.
Okay, yeah, it's 120 degree, 0.25. Okay, so doing 120 degree, it's similar in the amplitude as being -6 decibel, but if I only see this one, I have no idea that you are changing the phase or the time instead of the amplitude. Whoa, whoa, this is brain destroyer. Okay.
And that's exactly why the Nyquist theorem is like a non-inclusive on the Nyquist frequency. It's just a minor detail, but it's something that is interesting to point out.
And the other important thing, I can see that even when the greens is 0.25, I can see that the peaks are 0.5. So this means that if we have a digital to analog converter, in the analog conversion, the peak of this Nyquist frequency is 6 decibel higher than what the sample amplitude is showing. Oh my God. Okay.
Except that remember that we don't really know if it was that version of this version or this version. So like during the reconstruction, the Nyquist theorem will also apply, and we shouldn't be reconstructing the Nyquist frequency just because we don't know whether it was one or the other one.
Any digital to analog can reconstruct all frequencies except Nyquist.
Up to Nyquist minus
-1. Okay. Wow. Amazing. Okay.
Right.
Thank you, Juan.
I'm gonna let you guys keep going unless there's a question about this, but we can also talk about it at the end.
I have many questions, Juan. However, Oscar should explain a lot of topics right now. Okay.
Yeah, I want to share my screen just to go deep a little bit into right now. This is a slide that is telling you that we are right now trying to see all this great stuff that Juan Sierra was showing us. But in this case, what we're gonna do is to get into the smart option section, just to let you know that, of course, we can just do two sample rates into smart. One of them is 48 kilohertz and the other one is 96 kilohertz. So this is because we want to analyze what is happening with the FFT size and the sample rate into some kind of window that is called live input response. So in the left side of the screen, you're seeing right now the option windows, and in there we could see that we are using the tab called transfer function. And if you go all the way to the down to a lower section, you could see that we have over here the live input response FFT size. And you could see that we can select from 2K all the way to 32K. That is telling us about the amount of samples that we are using. And by considering that samples and also considering the intersample time when we're using 48 kilohertz as a sample rate, we could just do the math to get the amount of time that we're going to be able to see. So this is about a little bit of math, but the most important thing is that you realize that by increasing the FFT size, you're going to get a more view in terms of the time. And one very important thing to notice is that if you are running your smart session at 48 kilohertz and now you want to go to a 96 kilohertz sample rate version, you need to just consider that you're going to have the same options in terms of the FFT size, but the number that you are going to get in the time domain are going to be half of the ones that we were using with the 48 kilohertz sample rate version. So this is just a very quick overview, and you need to remember that if you are working at 96 kilohertz, the numbers are going to be half of those ones that we are having with 48 kilohertz. And if you want to see a little bit more of this, in this slide, what we are seeing is just the input response in live, the live input response windows, and we're using, again, the 48 kilohertz on the top and the 96 kilohertz version in the bottom. And right now we're using the 2K FFT size version. So as you could see, if you are selecting 2K, you're going to be able to analyze around 42 milliseconds total in terms of time. Actually, the right number is 42.67 milliseconds. And by having this number, because you're using 2K option, you need to realize that you're going to do the math by dividing this number by 2. And when you get those numbers, those are the numbers that you're going to be able to analyze as a complete version on this window that is telling you that over the vertical axis, you're having the amplitude of the input response, and over the horizontal axis, you're having time. And right now, if you see over here, we are getting like a 0 milliseconds, zero as a reference. And if you go all the way to the left, you're going to reach minus 20.13 milliseconds. And if you go all the way to the right, you're going to get plus 21.30 milliseconds. So this is the option of 2K as FFT size. And if you want to convert these numbers, these time numbers into meters, you could see that we are going to be able to analyze from minus 7.25 meters all the way to 7.25. Of course, we don't really talk about minus something in distance, but this is just like an overview of what you're going to be able to see in terms of the distance. So the default window actually is half of this number to the left and half of this number to the right. So that's why you are seeing a little bit more of minus 10 milliseconds to the left and a little bit more of plus 10 milliseconds to the right. And well, remember that if we are working not in 48 kilohertz, but in 96 kilohertz version, you need to think of all of these numbers and divide it by 2, and you're gonna find the right numbers for the 96 kilohertz version. Okay, so instead of have a total amount of time of 42 point something milliseconds, you're gonna be seeing just 21.33 milliseconds. Same thing with the default range of the windows in terms of the input response live. You're gonna see just minus 10 milliseconds, sorry, minus 5.32 milliseconds up to 5.33 milliseconds to the right. So this is the option of 2K. So if we move on to the larger options, that is 32K, you're gonna see that the numbers are gonna change, of course, because we have more samples to analyze. So that means that we're gonna be able to analyze around 682.67 milliseconds. And remember, if you divide this number by 2, you're gonna have the amount of total time that we are gonna be able to analyze all the way from the center to the left. And then remember that the center is our 0, that's a reference. And the same amount of milliseconds is gonna be the maximum number that we're gonna be able to analyze to the right. And the default window, again, is half of this number. So in this example, we're seeing that we have a little bit more of minus 170 milliseconds to the left and a little bit more of 170 milliseconds to the right. So that is the default view. And again, if you wanna use this not with milliseconds, but with meters, we are around more than 100 meters to the left and the same amount to the right. And as the example that we just see with the 2K version, if you are dealing not with 48 kilohertz, but with 96, you're gonna be able to just analyze half of these times or distance. So if we are thinking of this number, when we are in 96 kilohertz, we're gonna see just half of this all the way to the left, that is 85.32, and the same number, or kind of the same number to the right. So the total amount is gonna be half of what we were analyzing when we were working with the 48 kilohertz version. So this is just something that you need to realize to figure out what is the best that you can see depending on what you are measuring. So in this slide, what we are seeing is like a small review of all the options that you are gonna find in the live input response section. And as you could see, we are using different colors to let you know what is gonna be the time range that we're gonna be able to analyze by using one of these options. If we go, for example, for 2K, you're gonna be analyzing just this small amount of time. Right now we have this kind of dark green line that is telling you that you are gonna be able to analyze by default from minus 10 milliseconds to plus 10 milliseconds when you are using 2K as an FFT option. If you could see, we have again now like a light green line version over here, the same line over this area, and that means that you're going to be able to go all the way to the left or to the right by using 2K, and you're going to be able to see around minus 20 milliseconds all the way to 20 milliseconds in the positive sections. Same thing with another example, let's say 16K. If you see, we have like a dark red color lines over here. That means that we are using that time range as a default. You are selecting 16K, but if you want to go further than those numbers, you're going to be able to go around, let's say, minus 170 milliseconds to the left and the same amount of milliseconds to the right. And again, if you want to analyze this not in terms of time, but in terms of distance, you could see that over here we have the amount of distance that you're going to be able to see by moving your microphone or by moving your speaker if you want. So the same thing is going to happen on the lower section of the screen, but remember, we're using just 96 kilohertz to see all these amounts of time depending on what you are using in terms of the FFT size. And again, you have the code that is telling you what are going to be the meters that you're going to be able to analyze. So this is the view options that we are having in terms of FFT size. And now we can move to another section into the smart. And this section is called delay. Again, we are in the same windows that is called options, but now we are using the tab called delay. And in here, you can see another kind of set that we can use, and it is called delay locator. So the delay locator is having also an FFT size. And I want you to just see this as a different preset that we just saw with the live input response section, because this is the delay locator section of the smart that is going to be able to let you find where you input response in terms of the time. So by using a higher FFT size, you're going to be able to analyze more time to find an input response that is far away from your reference or for your zero as a reference point, starter point. Okay, so in the left section of the screen, you are seeing these options by using a 48 kilohertz version. You want to know that because here is the math, and with the math, we're having the intersample time that is around 0.02, 0.83 milliseconds. You could see that over here we have one sample, and one sample is around 0.02. That is kind of this number, of course. And on the right section, we're seeing just the same delay locator section with the same options, but right now we're using not a 48 kilohertz sample rate, but we're using 96 kilohertz. And you could see that if you are considering just one sample, it is around 0.01 milliseconds. So here you have the number. And again, let's just refresh a little bit. This section is to let you localize where is your filter in terms of your input response in terms of time. So because we have a lot of options, we do like a small chart with all those options. You could see that over here we have the FFT size, we have those numbers, but in smart, and over here we have the sample rate. And let me just move a little bit this. We have the theoretical time that we can just reach with this amount of samples. And as you could see, we have just highlighted some of these rows because we don't want to show all these options. I think that you are going to be working around these FFT size options. And I know that because I just, by doing some tests, I just realized that these options are around of what we are normally doing in our real life, right? So what I mean is that even when if you go into the manual of smart, you're gonna see that smart is telling you that if you wanna analyze an input response that is like 10 milliseconds away, you need to select an FFT size that has at least 3 times of that time. I mean, you need to use an FFT size that is telling you that they can analyze like around 30 milliseconds because of course 30 milliseconds is 3 times 10 milliseconds. So I did some tests and I realized that if you are using from 8K all the way to 512K in the FFT size section, you could find some times that are half of the theoretical time that you are gonna be able to analyze. So by saying that, I just put these numbers over here, and those numbers are the real numbers that you are gonna reach by having this amount of samples, I mean this FFT size. And for example, if you consider that the smart is having a 64 kilohertz as 64K, not kilohertz, as default, you're gonna be able to analyze around 642 milliseconds if you are running at 48 kilohertz. And if you are using a 96 kilohertz session, you're gonna be able to analyze around 300 milliseconds of the time to find your input response, your inputs. So if you compare this not in millisecond, but in meters, you're gonna be able, if you're using 64K, you're gonna be able to analyze, let's say, a microphone that is more than 200 meters. If you are running your smart session you're during your smart session up 48 kilohertz. And if you are running that session in 96 kilohertz version, you're gonna be able to analyze around 100 meters. So I think the default option, the smart, is a good one because you are having the option of analyze and input response that is around, let's say, a microphone around 200 meters. So that is enough. But if you want to have more range in terms of the distance, you can go higher in the FFT size domain. So let's do a small example. Is, for example, use an FFT size of 1K, and you see 1K is telling us that we are going to be able to analyze a delay, an impulse that is delayed around 7 milliseconds. So we won't be able to analyze more than 7 milliseconds in terms of the delay between our reference signal and our measurement signal. So if we go to a smart session over here, and I go to the option window, and then I select, instead of 32, 1K, remember that we won't be able to analyze more than 7 milliseconds. I click apply and OK. So I'm gonna run my smart session with this transfer function, and I'm having actually a galaxy here in my house, and I'm gonna select the measurement channel and add 1 millisecond of time. And of course, we could see, let me just draw a small, I need to do a small zoom over there. So you could see that if I just click over here and see the input response is around 1 millisecond, you could see in the top section of the screen. So if I click in find in my transfer function, you're going to be able to see that we are finding 1 millisecond of delay. If I click find again and again and again and again, you're going to see that Smart is telling us that your input response or your impulse is around 1 millisecond to the right. So we know that because we are going to be able to analyze up to 7 milliseconds. But what happens if we use not 1, not 7, but 14 milliseconds? So 14 milliseconds is out of our range of analysis in terms of the delay finder. So you could see that actually you have the impulse over here, and if you see in the top of this on the top of the screen, you're reading around 14 milliseconds. That is the time that we just add into our measurement channel, and it seems that we are going to be okay by locating that impulse. But if we click in find, you're going to see that right now it's telling you that you have minus 1.22 milliseconds. And if I click find again, you're getting minus 8.77. If I click again, it's a 1.67. So we are not being able to find our 14 milliseconds. So maybe you're thinking, oh, that's why you are using just one average. So let's use the true average. I'm going to apply and click, and let's measure this again. So as you could see, we're not getting our 14 milliseconds, and we are spending more time because we have more average to analyze. Over here, you could see the FFT size that we are using right now, and you could see that we are having 32 average, and we're not being able to find those 14 milliseconds. So you know, of course, that what we need to do right now, let me just click over on this and let's go back to our presentation, is that if we need to analyze 14 milliseconds, we need to go at least to 10K in terms of the FFT size. So if we go back and use 2K instead of 1K, let's use just 2K, let's use just one average. If I apply this, if I go and measure again the impulse, the delay finder, we're going to see that we are getting our 14 milliseconds because we have enough samples, enough FFT size to find our impulse in our 14 milliseconds range of time. So this was about what we can just do in terms of the FFT size into Smart, but right now Magu is going to tell us what is going to happen with another great software tool to use in terms of the analysis of the sound. So I'm going to stop sharing my screen, and now it's your turn, Magu. You're mute, Magu. You're still mute. Maybe we can just
Yeah,
unmute.
right. Okay, I was on mute.
Now we can hear you, sir.
Yeah, the problem is that I was asking Oscar, what are you saying, Oscar? What are you saying? And I have no idea. Okay, so now, do you see my screen?
Yes, sir.
Yes.
Okay, thank you, Marilyn. Okay, so Oscar has been explaining how to configure the time, location, and the time range for the input response in the software Smart 8. And my turn is to explain in other different alternatives. And for all these explanations, I will use a high-pass filter, fourth order at 1K. And I will do this in order that the input response, instead of be a perfect impulse, will show us like a tail, like when Juan Sierra was explaining us, we see kind of tail, we will see here the tail. So, and I have this thing that is blocking, okay, hide floating meeting controls, okay. And I have also this thing that I want to move all the way down here. Hold on, because I want to make this stop sharing. Okay. And do again sharing. I have a problem because my cursor disappeared when I want to make, okay, the faces of everybody here. Okay. Right now sharing and come back here, play. Oh, and hide floating meeting control. Okay, finally. Okay, this version, this alternative is called Open Sound Meter. It's made by a friend. His name is Pavel, and you have the link of the Open Sound Meter here in the bottom, and the email address of Pavel. And instead of using FFT size philosophy, he display in the bottom time range and amplitude range. In order to display time range and amplitude range, we have to do click in the window where we can see the impulse. And we can see here very easily, no, I don't see my cursor. Okay, well, then we can see the impulse that shows the tail, what I show to the right of 0, it shows the tail. And also we can see in the left, that is the scale, positive numbers from 0 to +1 and negative numbers from 0 to -1 in the amplitude. And we can see in the bottom right that it corresponds the -1 to the circle that shows -1 and the +1 to the circle that shows the +1. In the time range, we can see that the left in the time is -5 milliseconds and the right in the time is +5 milliseconds. So this is the way to do this in the Open Sound Meter. And time range, oh, hold on, okay. What is the maximum time range that can be displayed in the input response in the Open Sound Meter? Goes from -20 milliseconds to +20 milliseconds. I have to say that around 10 days ago, I have a conversation with Pavel asking him for have longer time range in the display, like when we want to see like a main system and a delay tower, surely will be more than that. And Pavel expressed that he will work on that. And we can see again, the amplitude range is still 1. However, what is the maximum amplitude range that can be displayed in the Open Sound Meter is ±2. So in this case, you can see that the impulse shows that the amplitude is smaller, but actually the peak of the amplitude is still 1. Okay, not working. So the peak of the amplitude is still 1, and we can see how the scale shows from +2 to -2. And what is the maximum zooming that we can do in the open sound meter? In this case, we go from minus 0.01 to plus 0.01. So you can see that we see a lot of detail in all these oscillations of the impulse response in the using the high pass filter. You have the code in the right. So if you take a picture with your telephone, this can send you to the website of Open Sound Meter, the QR code. Okay, the next alternative that we will explain is RITA. This is an analyzer made also by another friend. His name is Pepe Ferrer, and you have the link in the bottom. G Audio's Global Audio Solutions is his company. And well, RITA, in order to configure the time range and the amplitude range for the impulse response, use a different approach. Not the same as SMART, not the same as Open Sound Meter. So the first thing to observe here is that there are two displays in this analyzer, and we can define that the upper display can be amplitude, impulse response, acoustics impulse response, spectrum, and in the bottom one can be phase, live impulse response, acoustic impulse response. Okay, so in this case, I have defined to be both impulse response for help for the explanation. So how we modified amplitude and time range here, we need to go in the top right where you see the label RITA, and we have to click RITA. And after click RITA, we have to click preferences. When we click in preferences, we need to look for the label live IR. And when we are in the live IR, we will have the time range and the amplitude range for the upper screen and for the bottom screen. So, and I use right now a yellow box for the upper screen and orange box for the bottom screen. So you can see here into the center that we have the amplitude range, the time range, and the smallest one in the time range is 25 milliseconds, and the larger one is 400 milliseconds. And we have also an automatic function that the software automatically will define what is the time range. We have also in the right window, what are the range for the amplitude range. The amplitude range can go from 0.1 to 10. So this is the amplitude range, and also can be in automatic. We have also, we have seen here that the upper screen is the amplitude range 0.1, and the bottom screen is the amplitude range 10. So this means, as you can see by all the indicators, that the upper screen plus 0.1 to -1, the impulse response is not fit in the screen. The screen is too small for that. And in the bottom screen, the range is 10. So the impulse response looks very, very little, but it's the same information. It's like in the top screen, we are doing a zoom in of the amplitude, and the bottom screen is that we are doing a zoom out of the amplitude. How we learn how to modify the time range, and now in the top screen we have 25 milliseconds time range, and the bottom screen we have 400 milliseconds time range. So this is like in the top one we have like a zoom in time, and the bottom one we have a zoom out in time as the default when we turn the analyzer after the configuration. However, most of the analyzers, when we automatically compensate time, set the impulse in the center of the analyzer. This software RITA is not doing that. We have to use this hand icon and then click in the screen to move the impulse to the left or to the right. So you can see how right now the real zero positions is being manually shifted to make the impulse to look more like in the center. And in this case, using the magnifying glass icon, if we click on that, we can define a range using left click in the cursor, you define the range. So right now in the range, we can do a more dramatic zoom in the time with the software RITA. And you have the QR code in the right, so you can take a picture with your telephone and this will bring you to Global Audio Solution website. So how we configure in another alternative, again, is my friend Thomas Neumann, and Thomas Neumann software is SatLive. And in the SatLive, when we enter into the input response graphic, we have by default two screens. The upper screen is the custom time range, and the lower screen is 10 times zoom in. And you can see that this is a kind of area that looks like yellow pale color, and that area, it's actually the area that we see in the bottom. So how we configure and define time range and amplitude range. Okay, in the right of this analyzer, in the right below the bar meters, we have several options, and the first one is size, time size, and the smaller one is 50 milliseconds, and the larger one is 2.5 seconds. So we can see here, the upper screen is 2.5 seconds, and 10 times zoom in is the lower screen that is plus minus 250 milliseconds. And the maximum zoom in by default is the one that we originally, I choosing for this is 50 milliseconds time range, where the zoom in the bottom is 5 millisecond time range. How we define the vertical scale, we use a parameter called Y factor. But Y factor here works not exactly as you think. So in this case, if the Y factor is 0.1, that we can see in the top, is not that the scale will reach 0.1. The scale will be 10, but the magnitude of the impulse will be like 0.1 times when it says 1. So we will see here right now. The factor right now, you see in the right, the yellow box read 0.1, but the scale in the left reads plus minus 10. So the amplitude of the impulse still is 1, but right now it looks like 1/10 of what used to be before. And of course, the lower graphic is 10 times zoom in time. And this one is a Y factor 10. A Y factor 10 is like increased visually 10 times the amplitude, but the scale will read 0.1 to minus 0.1. And again, the bottom graphic, it has zoom in time of 10 times. Something additional in the configuration here that is pretty interesting is this. We can modify that the bottom screen, instead of be 10 times zooming in time, by default can be something different. How we do this? We do right click with the cursor in any part of the screen, and we select tools. After selecting tools, we go to the option impulse response zoom value, and we select the value we want. You can see that by default, I select the number 10, but we can have a zoom of 5, and we can have a zoom of 1000. And this is one more thing to configure here. Again, you have to do right click in the screen, and after doing this, open again the menu, and you can select auto adjust amplitude. So this means that the scale of the amplitude can be defined automatically by the amplitude of the impulse that the analyzer detects. Also, you have the QR code here that will bring you to SatLive website. And the last one that I will explain is the Meyer Sound Sim 3 analyzer. And in the Meyer Sound Sim 3 analyzer, how we modify amplitude and range. Well, this is the one that I know more, of course. And in the case of the sim, in the default, you have impulse response for the electrical part of your measurement, that is the processor. In the top and in the bottom, you have the impulse response of the acoustical part of your measurement. In this case, is through using the microphone, the measurement of the speaker. And you can see in the bottom that it reads analysis time and read plus minus 70 milliseconds. And okay, as you can see here in the arrows, the scale, the default scale in the amplitude, it's plus minus 1 for the electrical part. And you can see that right now the amplitude reads plus minus 13 Pascal per volt that the analyzer receives. This will change after introducing the sensitivity parameters of the microphone. Okay, so if we click in the left part, the symbol plus or the symbol minus, we can do amplitude zoom in or zoom out. Right now, you can see that the symbol minus is gray color, the symbol, so we click as many times possible. So this makes a zoom in of 10, zoom out of 10. So you can see that the amplitude of the impulse looks very, very little, but it still is 1. But right now the scale can do 10 in the amplitude. How we modify the time range? Well, to modify the time range in the sim, we have here 4 options. Plus minus 70 milliseconds is the one that right now is select, and we can multiply by 2, by 4, and by 8. So the maximum time range is plus minus 560 milliseconds. And how we can do after this value, zoom in, zoom out? Well, in the center of the screen, you can see again a symbol minus and a symbol plus. If the symbol minus is depressed, you have zoom out of time, and the symbol plus is depressed, you have a zoom in of time. In this example, you can see that when we are in zoom out, it seems to be only one peak in the lower screen. Is like one speaker. But doing a zoom in on time, we can see that there are 2 peaks. So surely this is 2 speakers, or this is a speaker plus a reflection. And you have the QR code for the Meyer Sound website. So now that we have seen how to modify in different alternatives of analyzer, amplitude and time, let's go and dig more in depth in how to understand the information. Okay, the first thing is that by default in most of the analyzers, the amplitude is not in decibels. The amplitude that we will see is linear. And the scale horizontal, it's the horizontal scale, it is actually time, is not frequencies like normally we see with frequency response analysis. Normally when what you are more familiar is to see amplitude and phase. In this example, we have amplitude in the top screen and phase in the bottom screen. And what we are measuring here is an XLR balance cable. So the XLR balance cable, it's 0 decibel of amplitude gain and 0 degree of phase shift. So in the typically scale of amplitude, we see decibels. And in the typically scale of phase, we have 360 degree range, that in this case, we have 0 degree in the center, 180 degree going up and 180 degree going down. So in the case of the impulse response, remember that the amplitude is the vertical and the time is the horizontal. But we have mentioned that the amplitude, it is not logarithmic, but is linear. And we have to understand that the upper portion, it's positive polarity, and the lower portion is negative polarity. And the larger the image that we will see, the larger the impulse that we see, means more amplitude. The shorter the impulse that we see is less amplitude. And because the scale is linear, this is what we have to realize. If the amplitude of the peak is 1, this represents 0 decibels. If the amplitude of the peak is 2, this represents plus 6 decibels. If the amplitude of the impulse is 0.5, it represents minus 6 decibels. It doesn't matter if the impulse is drawing up or down. Remember, up is positive polarity, down is negative polarity. But how large is that? This is the amplitude. And basically, if you want to convert the amplitude of the impulse into decibels, you read the amplitude value and do logarithmic time of that value, and then multiply by 20, and you have decibels. So the equation is 20 log of the amplitude value. And what about time? Well, in this case, the time scale, as we can see, is milliseconds, and the 0 is in the center, and 7 is to the right. And we can see how more to the right means increase of time, and more to the left is decrease of time. So now let's try to digest simultaneously impulse response and amplitude response. We are measuring not anymore a cable, but we are measuring an electronic device. And the gain of the electronic device is -6 decibels, as you can see in the bottom graphic, but the peak of the impulse is 0.5, and 0.5, as we have seen before, 0.5 corresponds with -6. And in the second example, the amplitude of the peak is 0.7, and 20 multiplied by logarithmic of 0.7 is -3 decibels. So you can see in the bottom graphic that the amplitude is -3 decibels. The next graphic shows that the peak is 1, and 1, as we have seen before, is 0 decibels. This is 20 multiplied by the logarithmic of 1 is 0 decibels. The next example shows that the amplitude is 1.4, and 1.4 is 3 decibels, as can be verified with the bottom graphic. And the top one reads linear 2 in the position of the peak, and 2 is 6 decibels of gain of the processor. Now, we have seen how it will be positive. Well, the peak of the impulse will go up. What is negative polarity? The peak of the impulse will go down. So how we identify time? Well, we have here 4 examples where we have 0 milliseconds of delay in the electronic processor in the top left, and in the top right, we have 1 millisecond delay. In the bottom left, we have 2 millisecond delay, and in the bottom right, we have 3 millisecond delay. In this example, we are measuring 4 signals. So what happens here is that I take 4 outputs of a processor and combine the 4 outputs and send to the input response of the analyzer. And you can see that the first output is +6 decibels because the amplitude is 2. The second output is +3 decibels because the amplitude is 1.4. The next output is 0 decibels because it's 1. And the next one is -6 decibels because the amplitude is 0.5. And we can identify what is the electronic delay in every one of the channels. So just reading at the impulses, we can decode, we can figure out what is the gain and the electronic delay in any one of the outputs of the electronic processor that we are testing. Now, let's go even more in depth because we will measure impulse response in the top right, and we will measure simultaneously amplitude and also phase. In the first example, we have a +6 decibel gain, and we can guess that because the peak of the impulse is 2 and the delay is 0. So this means that the amplitude of the processor in the bottom right is 6 decibels and the phase is flat, is horizontal because it's no delay. However, when we decrease the gain, and right now the gain shows 1.4 linear, this should be 3 decibels in the bottom right. And because we have 1 millisecond, we will see phase shift. So it's like phase rotation in the bottom graphic. And the first rotation, the first time the graphic of phase go back to the center is in 1K. 1K is the time period of 1K is 1 millisecond. That actually is the time delay of the processor. So everything corresponds. The next example, the time is 2 milliseconds. 2 milliseconds, by the way, is the time period of 500 hertz. So in the bottom right, we can see that the first rotation of the phase graphic is in 500 hertz. That corresponds with the 2 millisecond delay. And the amplitude reaches 1. 1 is 0 decibels. Something that we can see also here is that the longer the time delay, the higher frequencies shows by steps, drops of amplitude graphication. So this is the analyzer is exhibit error in the transfer function, and the red graphic, the coherence, dropped by steps. This is because the analyzer are using a method called constant Q transforms that basically use a smaller FFT size to the higher frequencies and exponentially increase the FFT size to the low frequencies in order to display the same number of data points per octave. So the next example shows 3 milliseconds of time delay. 3 milliseconds of time delay is the time period of 333 hertz. That is where we can see the rotation in the phase in the bottom graphic. And we can see because the peak of the amplitude is 0.5, so this means that this is minus 6 decibel of amplitude. But again, we can see the amplitude error and the coherence reduction by the constant Q transforms of the analyzer. Okay, so now we can see, like more in the real world, what you expect to see when you measure a speaker and a processor simultaneously in the real world. Okay, so in this case, this is a latency of the processor, and the analyzer identify the latency of the processor. That means the difference between input to output of the processor is 2.9 milliseconds, and the propagation delay, that is the distance from the speaker to the microphone, is 3.71 milliseconds. If we see the amplitude and phase before compensating the latency, you can see that we have one cycle in 345 hertz, that is 2.9 milliseconds time period. And we can see in the little box, that is the 2.9 milliseconds delay that shows the input response. And you can see the speaker also, the analyzer has not compensated the propagation, and the transfer function has error, and the phase is a disaster. So if we compensate the error in this analyzer, we have to click auto set delay. Then the analyzer compensate the 2.9 milliseconds latency and the 3.71 propagation delay. And right now the impulses are looking in the center of the analyzer, but the center of the analyzer is not 0. The center of the analyzer is already 2.9 milliseconds in the top screen and 3.71 milliseconds in the bottom screen. However, after doing this, we can see that, well, the impulse is in the center, amplitude shows 0 decibels, and the phase is correct, is horizontal, is flat. What happened to the speaker? Well, after compensating that, the frequency transfer function of the analyzer is correct, the coherence is correct, and the phase is flat in the mid and high frequencies, except in the low frequencies, because the high pass filters and low pass filters used by the crossover system introduce phase shift, that basically is phase delay. The lower frequencies proportionally are electrically being delayed compared to the higher frequencies. And the last part is how in the real world we can learn if after compensating the time, the speaker increase or decrease distance to the microphone. Okay, in this case, you can see a red color arrow, and the red color arrow is the position of the microphone, and we have a ruler that is telling the distance from the microphone to the speaker, and the propagation delay is 3.71, and the time is compensated. So now you can see that this is making amplitude and phase correct. So what happens if the microphone increases the distance? You can see right now by the red arrow that the microphone moves far away to the speaker, then the impulse moves to the right. And what happens with the impulse move to the right? We will see phase rotation. The phase rotation is telling us that the microphone is at larger distance than the initial distance, that is the one that is being compensated in the analyzer. And what happens if the microphone is moving closer to the original position? Well, the impulse response moves to the left of the center in this case, and the phase is very interesting. The phase shows rotation, but instead of the phase shows rotation down tilt, the phase shows rotation, and you will see up tilt. So the rotation goes in the direction up, obviously reading from left to the right. And how we identify reflections. Okay, in this one I have to explain that the picture that you see here, the camera is set in the floor and is pointed to the ceiling. And you can see speaker and you can see microphone, and the time propagation is being compensated in the analyzer. In the next image, you can see that I'm holding a book, and this book will make that the sound propagation will have a direct path and will have a reflection. The reflection is what you can see here with the label echo. And the reflection always is larger path because the direct sound is straight, and the reflection need to have a little bit of deviation. If the book increases the distance to the microphone, the echo increases the separation from the direct signal. So I am moving the book, and you can see how the peak is going closer or far away. And the last part, before Oscar start to do real live demonstration, is how we identify interaction with multiple speakers. Okay, again, we have one speaker, one microphone, one impulse, and we are in a position that the reflection from boundary like floor or walls is far away, so we don't see reflections here. But when we have two speakers, after having the second speaker, the speaker in the left is on access to the microphone, is the impulse in the center, but the speaker in the right arrives a little bit later, and this is the second peak that you see in the graphic. So this is the far speaker. Of course, that it's pretty hard to figure out if what you are watching, it can be a reflection or it can be a secondary speaker. So we have to do trial and error investigation, like with the processor and moving the microphone in order to discover if the second spike can be a reflection or second speaker. So now we are prepared for the nice part that is Oscar explaining this in the real world. Let me do stop share. Okay. So Oscar.
Thank you, Magu. I'm gonna share my screen and we're gonna go to this slide. And just to remember, we have another topic that is related to input response in the real life. This is input response versus bandwidth. And we talk about this topic when we did the Webinar filters in the real world. So you could see that we have a QR code just to let you go in to see this video if you want to refresh that information. So as Magu mentioned, we were dealing with a real world example. And in this case, what we were using is a regular size arena where you could see that we have main left-right system over here. Behind of those, we have the subs. And we also have a lateral system just to cover the lateral section of the seats in this arena. We are also having left and right subwoofers on the ground, and also some fronts that are going to take care of this near area in front of the stage. And because the main system is not covering the upper section of the arena, we're using a 3 delay system that you could see over here just to take care on over that area. So we're going to use this arena as an example in the real world, but of course we are not actually in that space. So what we did is like we were working with a lot of microphones around there just to see what is the best position to find where the input response is having the same amplitude. And that is a position where if you don't adjust the time between them, you're going to have a very, very bad comb filter situation. So we were moving around all those microphones to find the best position to analyze what is going to happen in terms of the delay time between the speakers. And I'm going to do 3 exercises to just show a little bit of this. So if you want to see what is going to happen with all this system into this space, so we have this prediction where you can see that all of the system are working right now. I mean, the main, the laterals, the front fields, the relays, and you can see that we have a very good shape of coverage. So the first example that we are gonna simulate with these 2 speakers is the main and the lateral system. So at this point, what we did is that just get the amplitude and the phase response from map3D with the propagation delay, and we put that response into the smart, and by following those amplitude and phase response that we got from map3D into the smart, we just be able to replicate what we saw in map 3D. So we're gonna simulate, and for this we're using 2 MM4 speakers. So at some point, one of these speakers is gonna be the main system, and the other one is gonna be the lateral, and in another example, one of those is gonna be the front field, and in another example is gonna be the delay. So we're going to move a little bit the settings for these 2 speakers in order to analyze our example. So the first one is going to be our main system and our lateral system. As you could see, we have over here the top view section, and you can realize that we have a mic position over here. And from that, we did a small arc just to show you that the lateral system is further away from the microphone than the main system. And you could see also with the milliseconds that we are getting for the propagation delays in terms of the mic position and these two systems. We're just showing the main and the lateral system because we don't want to spend your time looking around on this slide. So, and again, this is a small arena or a regular size arena, sorry. We have 132 meters over this section and 96 over this one. And we have a height around 50 meters, 50 meters. So it's a regular size arena. If you see this view from the side, from the back side of the arena, you could see that we are looking at the arrays from the back, and you could see the microphone from this position over there. So that is the best position that we can get to have the same amplitude in terms of the input response. And if you were the microphone, you're gonna see the system like in this image. So this is like a mic view position, just to let you know what we're gonna see if we were in that arena. So to do this example, again, what I wanna do is go to my compass session, and I did select my main and lateral snapshot. And right now, because we saw in the image that our lateral system is farther away from the microphone than the main system, we're going to use the lateral system as a reference. And for this example, we're going to use SMART. So everything was just set up to do this example. So I'm going to just click on my generator. I'm going to use this transfer function, and let me just see what we are getting over here. So right now, let me just click on here. I'm gonna stop for a while my video because I need to have
Oscar,
more.
maybe the FFT size. Oscar, maybe the FFT size of your input response of the display of the input response is so large that it took so long, so much time to be displayed.
Sorry, I couldn't hear you, Magu. Can you tell me?
Okay, maybe the FFT size of the live input response is so large because it took so much time to be displayed.
No, it was because I was in another window, Magu.
Okay.
Let me just click on find just to figure out what is the number. So it is around 88.50 milliseconds. That is good. So you're gonna insert that number, and I'm gonna store this as our lateral system. So now that we have our lateral system, we can go and switch to the main system. And as you could see, if I just do a small zoom over here, the impulse is to the left. So that means that it's arriving first, and we could see it also with the positive slope in the face that is telling us that it's ahead in time. So if we want to know what is gonna be our delay time between these two input responses, we need to go here and see our delta delay, and it's telling us that it's 4.92 milliseconds. So I'm gonna go back and I'm gonna write down 4.92 milliseconds. And if I go back, we could see that maybe a little bit less in time. So let me just go back and do just 4.9.
4.9.
Now it's good. You can see that the phase is really, really good. So I'm gonna start this trace as a main system. And now that we have these two traces, we can just add the lateral system. And you're just seeing that we have a very good outcome from the addition of this time. If we don't take care of that time, let's just remove this one. You're gonna see that we have two inputs over here. And of course, if we just draw a small line, you could see that the inputs are kind of at the same amplitude. So it's a good mic position. But of course, we don't want to have this result because, as you could see, we don't have that much energy that we got when we were in line and in time over this area and over the higher section as well. We don't have that much energy, and we have a count filter, of course. So
Oscar, it's a very nice example, because many times people ask, so what happens if I don't adjust the bloody delay? Well, we can see here, if you don't adjust the bloody delay, oh, you remove the graphic, okay. can you remove the blurry delay compensation? So what happens when we don't synchronize? Well, we can see here, we have a lot of comb filter, and this comb filter makes less summation in low frequencies, mid frequencies, and high frequencies. So if somebody says, I don't care to use time compensation, okay, if you don't care, is that you want to have a less powerful and clear and coherent system.
That's really true. So our next example is gonna deal with the main system and the front field system. As you could see, again, we have a mic position over here. That was our best option in this scenario. And we have, of course, again, a small arc, just to let you see that our lower section of the race is farther away from the microphone than our front field. So you could see as well this in terms of the delay that we are seeing over here. So we are just seeing the top view over here. You could see our main system, and roughly you're seeing our front field that is down there, and we are having our mic position over here. In this other view, we have our lower section of the array, we have our front field, and we are having our mic position over here. So let's go back, and now I'm gonna select not the main and lateral, but main and front field. So I click OK. And because we saw that our main system is farther away from the mic position than our field, we're gonna use this as a reference. And now we're gonna use not smart, but we're gonna use open sound meter. So everything is just ready over here. I'm gonna click play with my noise. So I'm gonna click over here. And now we are not able to see any impulse over the input response area. So why is that? Let me just move this a little bit because it's not letting. Okay. That is why. Why is that? That is because we are only allowed to see minus up to 20 milliseconds. If you go here, you can see that our estimated delay time for the propagation delay is around 33.71. If I click on that, we can just see that our inputs over here. I'm gonna start this, and we're gonna call main, okay? And now I'm gonna go back, and we can switch from main to our front field. And as you can see, we have another inputs over here. And again, if we just draw a line, we could see that we are having around the same amplitude in terms of the input response. So that's a good mic position again. And now if we just want to know what is the time that we're ahead in terms of the input response, what we're going to do is just go over here and see that our estimated delta delay is 14.52 milliseconds. So we're going to add that delay. It's going to be 14.52 milliseconds. If I go back, you're going to see that the input is moving over here. The phase response is good. So you're going to start this, and I'm going to call it front field.
Oscar, you are jumping from one window to the other so fast that I actually, when you introduce 14 point whatever, I didn't saw that. I still see 0. Can you go back just to confirm that you introduced 14 point? Remember that this is maybe 1 second in order that the graphic is zoom and refresh. Okay, 14.52, finally the same phase and amplitude, and we can confirm that the impulses are similar in amplitude because the microphone is correct. Okay, lovely.
Okay, now I'm gonna go back and add our main system.
And summation.
And I'm gonna start this one.
Wow, okay.
Our outcome. So right now we are getting this. This is good. But what happened again, if we don't take care of this number of our delay number, we go back and click 0 and then go back. We are gonna be seeing right now again two impulses over here. And we have cone filter, of course, and a reduction in gain in terms of the high section of the frequency.
Drop in amplitude
So
and
this is not a good idea. Let's go back and put our number. This is the magic number. And now we are really, really good in terms of our
perfect.
main system and our front field. And the last example that we are gonna see, let me just go back here. I need to see my window. Okay, this is the last example, and it is about our main system and our relay system, or sometimes it's called our delay tower in this arena. So what we see here is what are going to be our best position, that is around here. That is our best mic position for time align these two systems. And you could see again the small arc and the number that is telling you that the main system, of course, is far away from the microphone than our relay system. You could see also the top view over here. We have our main, our relay, and the mic position. And if you go to that mic position and see the systems, you're gonna see the relay system over here and the main system over that area. So let's go back and then use main and relay. And because we know that the main is far away, we're gonna select that as a reference. And now we're gonna use RITA. And we are all set up already with RITA to manage our measurements. So right now, the only thing I need to do is click on Gen just to get our zip. Okay, I hear our sweep, and you could see that actually we are having our magnitude response over here and our phase response over this lower area. And you could see that we have some amplitude response, but if I click on live input response, I'm not seeing any impulse response. Why? Because we are only seeing up to 100 milliseconds. So if I go to the preference in RITA, we can just go over here. I'm gonna change the thickness, and as well I'm gonna see our live input response in the down section of the screen, and I'm gonna select 400 milliseconds, and now
okay,
our impulse. And now we can just, if we want, a small zoom over here just to see the impulse over this area. And if you want to know what is the time for this impulse response, you need to go over this section, and you could see that we have time over here. And if I find that number, you're going to see that the amplitude response is now in a good shape. Our input response doesn't move a lot because RITA is always going to show you the real time in the live input response. But if we go to phase, we're going to see that we're in a good shape over there. So we're very good with our main system. And now we're going to switch to an engine number 2, where we're going to measure our delay. And of course, I need to go back to my processor. And instead of having the main system, I'm going to use the relay, or the delay, or the tower delay that we're using right now. If I go back to RITA and I click to do our sweep again, you're going to see that right now we're using this second row in the DSP domain, and we are having a little bit of some amplitude response over here, and a little bit more of the phase response. You could see we are arriving earlier. If we go to live input response, you're going to see these two inputs that are kind of the same amplitude, so it's a good position. And if you want to know what is the time for this first input response, it's about 88.08 milliseconds. So this is the time for the first impulse. And if you click on sync over here, you're gonna have the time for every single impulse. You click again over here just to synchronize with the second impulse, you're gonna see that our delta delays is around 115.48 milliseconds. So as you know, in RITA, we can just do something crazy things. As you may know, we can just select the channel and put some delay or EQ or whatever you want to do. And if I click over here where the delay section is, now we can see that the impulse is at the same position that the second one that we were having. And we can actually add these two signals together. If I go over here and click on sum, you're going to get that we just have a very good addition between these two systems. So what I want to do right now is to select this folder and right click over the zoom area, and I'm going to export that into response. And as you can see, we have the zoom over here. So we no longer need to add these two signals together. But what I'm going to do is just right click over here to import that input response. And now we are seeing just the addition of these two systems. So if I'm going to go to the next engine where we are going to have the addition of these two systems, because remember, we did this into the RITA, but right now we need to go out in the real world. So what I want to...
Oscar, what you have done is to use the calculation in RITA is not real processing because you have not gone yet to the galaxy. So right now, we can think this is the prediction of RITA of when you really do that. Okay, that's pretty interesting.
Exactly. And now I'm going to write down the same number that was 115.48 milliseconds in my processor. And now I'm going to open as well the main system, and I'm going to go back. And because we have this estimation that we did with RITA, let's just compare these two.
So now this is a real measurement.
This is a real measurement. And as you could see, if I double click over this section, you're going to realize that the addition is the same. So RITA is telling us what is going to happen in the real life. And of course, again, if you don't take care of that number, I'm going to go back and put 0 in the millisecond section. And I'm then going to go do a sweep again. I actually heard 2 sweeps, and you could see that we have again com filter and gain reduction over the higher section of the amplitude response. If you see the live response, we are seeing again 2 impulses that are telling you that we are not time aligned in that position. So
very amazing, Oscar. Very spectacular.
This is not a good idea. So let's go back and put our mic number, and let's just sweep again. And now we have just 1 impulse, and the phase is good, and our addition is just okay. So this was the 3 examples that we planning to have with you. I hope you enjoyed those ones. And now the only thing that I need to say is that if you wanna do some example like this, you can just go and see this video that is gonna tell you how to export data from Map3D, I mean the microphone data, into the smart. That's what I did, just to realize what is gonna be the numbers in terms of the propagation delay and the amplitude and the phase response. And by saying that, I think this is our last slide. So thank you everybody for being here. And well, I don't know if we have any questions.
So we did have some questions, but all of those were answered while you were doing a wonderful job at explaining impulse response. So Juan Sierra and myself, we answered those questions in the comments. That being said, if you have any additional questions, please populate those in the comments. We will be monitoring those. And while we're doing that, I would like to make use of the opportunity to make some closing remarks as we keep tracking the comments in the Facebook live stream feed. So as I said earlier today, a recording of this webinar will be available within the foreseeable future, as well as the previous 2 webinars in the series of real-world applications, such as filters and all-pass filters. And that means that I would like to express my gratitude to today's speakers, starting in reverse order with Juan Sierra Lozano, Meyer Sound test engineer. Thank you for showing your very interesting application that allows us to construct an impulse response and see how it changes when you change the amplitude values of the oscillators and the phase values. Great work. I would also like to thank Oscar Barrientos, Meyer Sound Technical Services Manager, Latin America, who just showed you some real examples using various analyzers that are out there, as well as Mauricio, Magu, Ramirez, who took us through the theoretical part of the IFFT, or impulse response, as everybody calls it. And that means that we've come to the end of the official part. We're going to have one more webinar in 1 month from now, if I'm not mistaken. And
Merlin, I think that the only two persons that know what I will say is Oscar and me, but I think nobody knows that Juan and Merlin are on vacation this week, and they thank you very much for being here because they are taking their very important vacation time to participate here.
thank you, Magu. So that brings us to the end. As I was saying this, I did not see any additional questions. So to all of you, I would like to say, please stay safe, please stay healthy, best to your loved ones. To my fellow Meyer Sound colleagues, thank you once more for doing this lovely webinar, and we'll see each other hopefully in 1 month from now.
Thank
Bye-bye.
you. Bye.
Bye. Bye. Thanks.
Okay. I stopped the stream and